So, reminder for everybody. So our first unit exam is happening this Friday. So it'll be happening here in this room. Bring your computers with you. We're going to be using that same Respondus lockdown browser that we did for the pretest on the prerequisite material. So if that wasn't working for you at that point, make sure to head down to IT, make sure that's working for you. There's a little like tester quiz on there, empty, but it should help you make sure that that lockdown browser is working. In terms of format for the exam, those of you who have already taken the practice test will know that it's the exact same format. So it's going to be 33 multiple choice questions, 3 points apiece. One question that's just 1 point to make it an even 100. You should pick the answer that it says to pick in that question. There will be one extra credit question on there as well. Questions about the exam format of the exam. Cool. So that's on Friday. Won't see you Wednesday because it's community day, but I will be around the rest of the week if you have questions. Swing by my office if the door is closed. Go ahead and knock anyway. Probably in there. And if I'm not in there, then you knock, then I don't answer. Not the end of the world. Any other questions? It's 100 total. So 33 questions, 3 points apiece. One question to make it an even 100. 3 extra credits. That's all multiple choice. Cool. Okay. In that case, we're going to cover our final topic on this little catch-up day, which is primarily, most importantly, going to be about osmosis, although we'll also take a little bit of a look at conductivity if we get there. Okay. All right. So hopefully osmosis, the idea of osmosis is familiar to you. When we're talking about osmosis, we're talking about the movement of water. And so it's a type of transport where we're moving water across a cellular system. Okay. So characteristics of osmosis. Osmosis is always a passive process. You're never going to have a water pump. It's always traveling down the gradient of water, right? So it's always traveling from areas where we have lots of water to areas where we have less water. Any cell, unless I tell you otherwise, has aquaporins in it. So any cell, unless I tell you otherwise, for the topic of osmosis, I will not. Any cell, you should assume that water can always cross the cell membrane. So any cell in your body, that's a very specific one for the kidney, water can cross the membrane. So this means that we can always have the movement of water under our baseline conditions. It's going to happen passively, it's going to happen automatically. This is not going to be affected by any of our membrane potentials, these electrical driving forces, electrochemical driving forces we've been talking about, right? So water interacts with charged particles, does not itself have a full charge on it. So we don't have to do that whole business when we're thinking about osmosis in the direction water will flow. All we need to think about is, where is there a lot of water? Where is there only a little bit of water? So essentially, we're thinking about a concentration gradient, right? So like a chemical driving force. So if we're looking here, right, situation that we got. We're going to start with a situation up here where we have pure water in our extracellular fluid. Okay, so our ECF out here, the solution that our cell is in, pure water. So absolutely everything surrounding this cell is water. That's the case. And in our intracellular fluid, our ICF, right, we have some water, but we have other things that aren't water. This means that our water concentration gradient, right, from pure water, that's lots of water, so high water concentration. Okay. And as soon as we have other stuff mixed in with the water, right, like other stuff takes up space. Okay, so as soon as you have not pure water, that's automatically going to be a lower concentration of water relatively. Right? H2O. Okay. So in this situation, where you put a cell in pure water, you're going to have automatic passive movement down that water gradient following its chemical driving force. So you're going to have water moving through aquaporins into your cell. So in this case, for osmosis, our direction for the flow of water is into the cell. Okay. So that's analogous to how we've looked at the movement of all our other substances in this unit, right? Except for we're paying attention to water. Now, the tricky new bit about osmosis for us will be that often when we're talking about solutions, right, like it's not normal in a chemistry class to say how many moles of water are in a vial, right? When you get concentrations for solutions, it's usually going to be telling you about everything that's in the water instead of about the water itself. So we're going to note here that there's a kind of inverse relationship between our solute dissolved in water and the water itself, right? So in this situation, the solute concentration of pure water was 0, right? And on the water side, here we had 55.5 moles of water. On the inside, in the intracellular fluid, we now have a slightly higher concentration of solutes, 0.3 moles here, and we're later going to talk about this measurement in milliosmoles, but we'll get there. Okay, so slightly more solutes, which corresponds to slightly less water, right? So this is a big number, so it looks similar, but notice our water concentration is lower when we up the solutes than it was for our pure water. It was a little higher over here. So usually when we're talking about osmosis, we're not going to mention the water concentration. What you're going to end up seeing is the values for the solute, right? So you're going to see there's lots of salt inside the cell. There's lots of salt outside the cell, right? That's the kind of setup you're going to get. So in your head, you need to relate that to this inverse relationship with water. Right? And know that if there's a lot of salt, that means there's only a little water. Right? If there's only a little salt, that means there's a lot more water relatively. So I think that that can be the portion that's trickier when we're thinking about osmosis. It's also why we often think, instead of doing this business about thinking about the water concentration gradient, sometimes we'll shorthand it in our minds and just think about salt or solutes as pulling water towards themselves. And if you think about it as a pull on water, then you can skip that like twisting inverse relationship in your mind. You have the same answer, thinking about it in a slightly different way. But they're related to each other. They're telling you the same information, just in a different way of looking at it. So when we are talking about water solute in physiology, we do get a little bit more specific. We talk about osmolarity, we talk about osmolality later on. We're going to give numbers using this osmolarity for a lot of different tissue types to express their kind of total solute concentration. Right? So sometimes you might want to know specifically how much glucose is there inside a cell. But sometimes if you're thinking about osmosis, you're going to want to know, okay, how much stuff, how much glucose, but also how much sodium ion, how much potassium ion, how much chloride ion, adding it all together, if what you're interested in is the water specifically. Okay. So when we talk about osmolarity, we're talking about the total solute concentration inside a solution. We're thinking about all the stuff that's dissolved in your water. And we're keeping in mind that any solute, so any particles, any molecules, or whatever, they're displacing a little bit of the water, right? So as soon as you have the glucose in there, it's a little less water. If you look at the percentages, right? If you put some salt in there, it's a little less water than there was before when you look at the composition of the whole solution. Okay. So the relationship if we're looking at how to go from our moles of a solute to how many osmoles we're going to measure when we're doing this focus on water, and we're putting together all our solutes, it's going to depend a little bit on what specific molecules are in that solution. So the osmoles are going to be adding everything together, but we're going to think one by one to see how they kind of add into place. Okay. So we're going to start with a solution in this first example. It's just glucose and water, right? So if we have just glucose and water, have 0.1 moles of glucose, okay, in our water sample. Okay. This is going to correspond to 0.1 osmoles, right? So the os is telling you we're thinking about osmosis, we're thinking about the relationship to water. So within that, right, it's 0.1 osmoles in 1 liter of water. Okay. Might immediately kind of trigger you in your mind why we give these numbers in milliosmoles instead, right? Give them in milliosmoles instead so we don't have to work with too many decimals, right? A milliosmol is a thousandth of an osmol, so we can just multiply across and get our easier to work with numbers when we're looking at cells. So that's all that is just a standard unit conversion from our osmoles to our milliosmoles. So if you're looking at something like glucose, right? So something that's all covalently bound to itself. Very simple, 0.1 mole to 0.1 osmol, right? Directly, same number across. If you're thinking about it and honestly bound compound though, you're going to have to take into account that those ionic bonds, they dissociate in water, right? And we get 2 ions where you have just like 1 crystal before you put it into the aqueous solution. So if instead we start with some salt, right? So if we start with 0.1 moles of sodium chloride, sodium and chloride, when you drop them into water, they're going to separate out from each other, right? So we're going to end up with our sodium ions, right, positive, and our chloride ions negative, separate, each of them kind of taking up their own space. Okay? So this means that if we're looking at an ionically bound compound like this, we're going to multiply the effect, basically, right? So we're going to consider that from that original sodium chloride, right, you have 0.1 moles of sodium chloride, which means you had 0.1 moles of sodium and 0.1 moles of the chloride. So when we look at the solution with respect to water after they dissociate, you got to add those together. So now instead we have 0.2 osmoles in a liter of water. So we're adding things. If we then wanted to look at a solution where we have both these things, right? We have the glucose and we have the sodium chloride, we'd keep adding, right? So if we wanted to know what the osmolarity of a solution is with 0.1 moles of glucose, but also 0.1 moles of sodium chloride, we'd add that 0.1 mole of glucose, 0.1 mole sodium, 0.1 mole of chloride, and we get 0.3 osmoles total from those 3 things. So we could just add them together and look at that total osmolarity, right? Right, so that plus that, giving us a total of 0.3 osmoles. I'm telling you that because when you get measurements for cells, right, it's corresponding to adding up all the things that were inside that solution, inside the cell in the ICF, all the things that were out in the ECF, right? And the typical cell is going to have an osmolarity of about 300 milliosmol. So that's going to be our normal baseline number for osmolarity of cells in the future. Yeah.
So you say when there's a sodium and a chloride 0.2 osmoles,
Mm-hmm.
but then with just 1 mole of glucose, it's only 0.1, but wouldn't a glucose molecule be bigger like an ion? So why would
That's a great question. I don't know the answer to that. That's a great question for a chemistry professor, or maybe a physiology professor. Somebody can go ask that. That's how it works. That's how the math works. I learned the rule, but not the explanation for that part. Oh, speaking of questions, I didn't look up an answer, but I did talk about this with Dr. Schlater about the glucose transporters you asked. Yeah, she was suggesting, we thought that maybe if you left all those glucose transporters in, that like they're specifically in like skeletal muscle and stuff, so they might start to hog all the glucose. And if you didn't have enough, maybe your brain wouldn't get glucose or something like that. Did you find a better answer? Did you look for it? We talked about it at happy hour. We had fun. That's what we came up with. Was I not supposed to say that? Sorry, guys. That's the kind of conversations we have. How about glucose transporters? All right. Anyway, so bringing it to osmolarity. So these are hopefully some similar terms that you've seen before. So probably before you saw them as isotonic, overtonic, hypotonic. This is a similar concept. It's just tying it specifically to this number that we use to measure osmolarity. Okay, so if we describe a solution as isoosmotic, right? So isoosmotic, we're going to do this middle one first, right? So in an isoosmotic solution, this means we have the same osmolarity inside our cell as outside our cell, right? So that iso is for like the same, identical, right? So you can see that anytime we have water come into the cell, we also have water leave the cell. So everything just kind of stays the same, stays normal in an isoosmotic. In a hyperosmotic solution, so hyper means more, okay? So say we have our typical 300 milliosmoles as our osmolarity inside our cell in the ICF, in the intracellular fluid. In a hyperosmotic solution, we're thinking about something like, pick a number, I'm going to pick 500. Okay. So something that has more solute dissolved in it. So 500 milliosmoles. Okay. All right. So hyper always means more, extra. Right? So in this situation, if our solution, all the components of the solution could move, right? The solute, maybe we'd have it move from the outside to the inside, right? So if we were tracking the solute, and I told you this was all due to sodium or something, you'd have sodium moving into the cell. But in this situation, we're tracking osmolarity and we're tracking, specifically, we're thinking about solutes that can't move, right? So maybe there aren't the appropriate channels. Maybe the channels are closed. Maybe we don't have the right transporter, right? We're blocking the movement of the solutes that give us that osmolarity number. So in this situation, right, when we can't have those solutes move, we're going to see water moving, right? So we have water moving from where there's relatively more water inside the cell, right? So inverse, right? There would be a higher number for water inside the cell versus a lower number outside the cell, inverse to this situation with the solutes. I like to think about it the easier way, where we just think about that large amount of solute pulling water towards it, right? So that water moves towards this area of higher osmolarity, getting pulled by the solute. Because our overall goal, right, in life, in chemistry, whatever, is to reach equilibrium, right? So if you have water moving towards this area of high solute concentration, it's going to water it down, right? And if it could water it down enough, eventually you'd have equal osmolarity inside the cell and outside. Right? So that's why water gets pulled towards this higher solute concentration. The opposite happens in a hypoosmotic solution. So hypo means low. right? So in this example, we're thinking that typical 300 milliosmoles inside the cell is, let's say we have pure water outside the cell, right? So pure water, right? So 0 milliosmoles. Osmoles. So in this situation, the pull is larger from that 300 milliosmoles inside the cell. So water moves in towards that higher solute concentration. The result is a cell that swells and potentially even bursts. So that lyse means it bursts. So we could get a cell getting so big it actually bursts and dies in response to a super low solute concentration surrounding it. All right. So we're thinking about solutes as pulling on water, right? Another way we'll see this expressed is through osmotic pressure. So formally, the osmotic pressure is how much like you have to push the water against that pull from the solute, right? So it's the amount of pressure you need to apply to stop water from moving. So this is pretty much the same as our previous situation. We're just expressing it slightly differently, right? So in our typical setup, right, this is actually still that example from the very first slide. So we're thinking about a solution. We're on our first side. We have 0.3 moles of solute over here. This is going to give us our 300 milliosmoles there. Outside, we've changed it a little, right? So now we're going to have 0.5 moles here on side 2. So we've got 500 milliosmoles. Right, so we can see that the higher concentration of water is higher on the side where we have low solute concentration. It's lower where we have a higher solute concentration. Right? So our osmotic pressure could be expressed literally as a pressure here. Right? So here we can see that we have a lower osmotic pressure here with this lower solute concentration, a higher osmotic pressure here with this higher solute concentration. So these are different types of measurements and numbers that we could attach to things, but conceptually, they're all describing the same situation. They're describing a situation where a high amount of solute concentration pulls hard on water, right? Because there's less water there, because it's pulling hard. You want to push to stop that pull. You need to push harder than you would in a situation where you have less solute. Right? So this whole picture is still just about that pull of solute on water. That pull on solute is related to the water concentration itself. So when we talk about movement, we might also express that difference as a gradient. So if we say we have an osmotic pressure gradient, all we're saying is that we have a region where there's more solute one place, less solute another place, and this is creating a difference in the pull on water, and therefore on the push related to water. So if we wanted to express this gradient, we could just subtract. So we could subtract, since we're talking about a pressure gradient, that lower pressure, we'd subtract it from the higher pressure, seeing that this is kind of like our pressure and our force per movement. And I won't make you do those pressures, but that idea of osmotic pressure gradients will come back in the future. So the reason you've seen this referred to as chemicity in the past is that there's a little bit of a detail that has probably been erased in your courses up until this. So when we're thinking about all these things dissolved in water, inside cells and outside cells, some of those things might be able to cross the membrane on their own. Some of them might not. So there is a difference between permeant solutes, the ones that can move, permeant, and impermeant solutes, the ones that can't get across the membrane. So tonicity is more relevant when we're talking about basics of osmosis, because tonicity is referring not only to the osmolarity, but specifically to the osmolarity caused by impermeant solutes. So when we look at tonicity, we're going to see a situation where those solutes are never moving across the membrane. But sometimes in physiology, we'll see a setup where there are solutes that initially contribute to osmolarity, but then themselves are able to move. And that's why there's a subtle difference between. So you want to remember, tonicity is impermeant solutes is the thing to remember here. So here we have an example kind of showing the difference between the osmolarity and the tonicity. Okay. So in this example, we're looking at our impermeant solutes in purple, and we're looking at urea in yellow, which is a permeant solute, so it can move. Okay. So on the left-hand side, we're looking at something that is isoosmotic, right? So isoosmotic has the same overall concentration if you add up all the solutes, but it's not a situation that is isotonic, right? So it's not isotonic, because isotonic means we'd be looking at just the impermeant solutes, right? So we've got the same osmolarity on either side. So this is isoosmotic. But if we look at the tonicity, right, we have a tonicity where we have a high concentration of impermeant solutes inside. We have a lower concentration of them outside, right? So actually we have a hypotonic solution. Okay. So these two concepts don't always get you the same answer, right? So what would happen in this situation? Urea can move, right? So urea, in this case, the yellow dots are all outside, and there are none inside, which means that there is a concentration gradient for urea, which means there is a chemical driving force on urea. So urea itself will start to move, right? So those yellow dots are going to start to move inside the cell, right? And you can see on this figure B that that's happened, right? So now we've got some yellow in here, okay? Right? This has raised the total osmolarity of the inside of the cell, right? So now we're above 300 milliosmoles inside the cell, because now we have that impermeant solute, and we also have the urea, okay? So now we have a pull on water, right? Because now, in addition to being a hypotonic solution, it's now a hypoosmotic one. So water moves in, trying to water down the contents inside the cell, trying to get us to an equilibrium, right? So the total equilibrium state that like would be the goal, if we could get there, right, would be to have an equal distribution of those purple dots inside and outside, as well as the equal distribution of the yellow dots inside and outside. And that's the situation in which water would not move. Water is moving because we don't have this equilibrium state. Right. So that's why we sometimes separately refer to whether something is isosmotic or isotonic, right? We're specifying a little bit about what is driving this effect. And sometimes we'll get into these nitty-gritty details. For now, you can think about them as somewhat equivalent as concepts, right? The only difference that I want you to be able to trace right now is to just know when I say tonicity, I'm referring to impermeant stuff. I'm talking about osmolarity. I'm talking about everything. I won't expect you to walk through what we just did in that figure. That's for the future. Okay. So here's a table from your book talking about some of the definitions of these different concepts. So you can see that difference is about impermeant solutes versus all our total solutes. Let's say total concentration. So everything for osmolarity, only impermeant stuff for tonicity. You can notice that when we see ISO, actually everything we're comparing it to 300 milliosmoles, right? So that's our baseline for a cell. Okay. So ISO means the same in case of cells. This means 300 milliosmoles. Hypo means lower, less than 300, less than 300. Hypertonic or hypoosmotic means greater. Greater than 300, greater than 300. Future, sometimes there will be complexity. If something is high in its osmolarity, but not so much in its tonicity, there will be a little bit of shifting. But for now, we're just going to focus on equal, less than, greater than, just knowing that the general difference is in the permeability. Okay, so we're going to think about both of these as creating a column for our purposes. Okay. Question after. So the fundamental thing that I'm going to want you to be able to do with this stuff is to be able to think about, okay, if I give you solute concentration, or if I give you osmolarity for the inside of the cell or the outside of the cell, I want you to be able to tell me which direction the water is going to move. So it's going to move into the cell or out of the cell. And then other than that, we want some basic definitions about tonicity and osmolarity. We want to know that little basic bit about how we add up to get total osmolarity. Glucose, we just keep its own number on it, right? So 0.1 moles, 0.1 osmoles. But if we have something ionically bound, we have to double it if it splits into 2. If the word split somehow into 3, we triple it because that's a total number. So another thing that happens to be the case in your body, right, is that because we have this relationship between the movement of water and the distribution of solute, this means that we can actually change the size of cells when we see the movement of water or when we distribute solutes differently. So what we're looking at here is the relationship between volume and osmolarity. Right, so here we can see a cell volume here. We're starting with our original volume, so V0, right? So we've got a typical normal cell size here, our starting cell size in the situation where we have 300 milliosmoles inside, 150 milliosmoles outside. So we're looking here at a hypoosmotic solution here. Okay. So we can see this difference between the ECF, where we have less solute, more water, and the ICF inside, where we have more solute, less water. So we know this higher osmolarity, this higher concentration of solutes, pulls water in towards it. until we reach an equilibrium state where we have the same osmolarity inside and out. Okay. So we can see that the cell physically expanded as we drank in all this water. In fact, it doubled in size, right? Right. So originally we had a situation where the osmolarity of the cell's intracellular fluid was double that of the extracellular fluid. To get to equilibrium, we double that size of the cell as we pull water in. So we have this cool relationship between those solute differences and the volume of the cell itself. Okay. So here, when we're looking at B, we see the opposite situation, right? So here we have this hyperosmotic solution outside, so very high osmolarity. In fact, we're double the inside of our cell, but now we're double on the outside, right? So as water moves out of the cell towards that highly osmolar region, this cuts the cell in half, right? So it's the flip side of this ratio in our original state, right? So to get to that equilibrium, 600 and 600 on both sides, the cell shrank in half. And that's just a neat fact that happens to be roughly true. Fine a little bit, so we're going to take a quick look at an epithelial cell, okay, as we start to think about transport. Right. So when we look at epithelial cells, if you will, regularly, because our epithelial cells line all your body cavities and they line the outside of your body itself. So if we want to transport something all the way across the cell layer, all the way across epithelium, we're going to have to go across two membranes. So we're going to have to go across an apical membrane on the top. So the top of a cell is the apical part. And then we're going to have to go across the basolateral membrane. Baso for bottom, lateral is hedging our bets, lateral means sides, right? So we're going to have to go across an apical membrane, then across the basolateral membrane. We're defining that basolateral membrane as the side facing the blood. So the apical membrane is always going to be facing whatever is outside of your body. So that could be the air, but it could be like the contents of your gut tube, right? We discussed in that initial kind of schematic drawing of the body that sometimes things that you might initially think of as being inside your body are actually still kind of in equilibrium with your external environment. So the reason we have to draw things across both the apical membrane and the basolateral membrane is that in our epithelial tissue, you have tight junctions between neighboring cells. So tight junctions, think holding them tight, right? So they're like really like a kind of zip locking them together, right? So you have an impermeable barrier between the cells, meaning you shouldn't be able to have stuff like sneaking through the sides and not going through the cells. And that's a characteristic of epithelial tissue. Okay. So for those of you who took bio of the cell, this actually might be pretty familiar because you looked in one of your problem sets, I know, at the function of the gut tube as it relates to transport. But for everybody, we'll walk this through together, right? So one of the ways that we can have solute overall transported across epithelium is by powering things on the basolateral membrane with a sodium-potassium pump. So here we see our sodium-potassium pump on our basolateral membrane. Okay. So here on our sodium-potassium pump, we can see that our sodium is being exported from the cell. And in fact, it's going towards the blood here. Potassium's coming in, right? So potassium is coming in. It's not even, right? Our sodium-potassium pump is actually a little bit electrogenic. So in fact, we're making the cell a little negative on the inside, so we're influencing its polarity. But for our purposes right now, what we're going to notice is that this is creating a situation where you have high sodium on the blood side over here in the interstitial fluid. You have relatively low sodium inside. And because we've been pumping sodium out, this means that you probably have relatively higher sodium also on the opposite side of the cell, on that apical side. So we've just created a sodium gradient that is going to be able to power movement of things across our apical membrane. We also created a neat, nifty little potassium gradient here. Our potassium gradient here, we can see that we've released with a potassium channel. So this is just a normal old potassium channel. It's going to let the potassium kind of keep cycling in our sodium potassium pump. But we're going to do something nifty with our sodium up top. Okay. So up top on the apical membrane, I'm sorry, on the board, the captains here have resized themselves, but hopefully they're okay on your slides. Okay, so on the apical membrane, right, we know that we have high sodium outside, lower sodium inside, higher sodium outside here. So on that apical membrane, one of the ways that we're able to bring glucose into our cells is through co-transport with sodium. So we are actually able to use this sodium to pull glucose from your gut tube, from your intestine, into our cell, right? So this is an example of secondary active transport because we're working with a situation here where we have relatively low glucose, right? You didn't eat a lot of sugar, you just ate a little sugar, low glucose here in the lumen of your gut tube. You've got some glucose in your cell already, right? So you have relatively higher glucose. You've been making ATP with it, you've been doing stuff. But you want to soak up all of that glucose. So it's active transport because we're going against that glucose gradient. We're going from low to high. It's secondary active transport because we use sodium moving down its own gradient to pull glucose along with it. So this is our sodium-linked glucose pump up here, which is why I didn't focus on the previous slide where they'd drawn it just as a sodium channel, because actually we're going to use it for this larger purpose. Right. We are moving towards this area of low intracellular sodium. We've got low sodium inside the cells because we've been pumping sodium out across that basolateral membrane. This is creating that gradient in for sodium. And so sodium wants to come into the cell. Maybe it leaks a little bit, but we're also using that flow of sodium through this glucose pump, this sodium glucose co-transporter pump. We're using it to do secondary active transport to pull glucose into our cell. Okay. This is all written out here. All right, so we can see already here our sodium potassium pump was an example of primary active transport. Our glucose sodium pump, where we're using that gradient of sodium, right, is our secondary active. With the glucose, the way we're going to get it into the blood is by going through a carrier protein. So we're going to see this higher level of glucose going towards this rather low glucose in the interstitial fluid. But we've got to go through a protein to do it. So it's going down its gradient. So this is the favorable direction, but we need a protein to do it. So that's why it's facilitated diffusion, which was one of our passive transport types. And then that movement of potassium through that channel would be our ion channel diffusion form of passive transport as well. So these are all the many things that have to be happening in a cell when our goal is really just, let's get our glucose in the blood, right? So all these different types of transport work together to get glucose from your gut, where you're digesting your food, into your blood, where that glucose can be carried around and distributed out to your different cells. So that's why it's important to know each of the types of passive and active transport, but also to realize that they work together when we're transporting specific things. We're about at time, so we'll leave it there. So our exam content will also stop there. And next time we pick up, we'll start talking mostly about neurons. I'll pull back in the part because it's the last little bit that you need to know as it